The electric charge is a property of matter. In the world around us, charged objects have unequal distributions of positive or negative charges. For example, we are rubbing a balloon with the wool cloth, and the wool cloth sheds electrons onto the balloon. Next, we rub a glass rod with a silk cloth, and the silk cloth takes away electrons from the glass rod, giving it a net positive charge. When the balloon and the glass rod comes in contact, the negatively charged balloon is attracted to the positively charged glass rod. So as you can see in this example, like charges repel and unlike charges attract each other. But why exactly does this happen? Well, this is a property of nature, and it has been observed by physicists for a long time. In fact, the behavior of charged particles can be answered by quantum electrodynamical equations. Conductors easily allow electrons to pass through them. They have electrons that are comparatively free to move inside the material. Examples of conductors would include metals, human, and the earth. For example, most households have a grounding rod, which is a copper grounding device connected to the house's electrical service panels. They conduct unpredictable surges of electricity, such as from electric strikes on power lines, from the service panels to the ground. The earth is an enormous conductor and electron reservoir. Insulators are highly resistant against the passage of electrical currents. Most nonmetals like glass, porcelain, plastic, nylon, wood, and rubber are insulators. That is why electrical linemen wear boots with rubber soles so that the shoes can prevent electricity to pass through the person and go to the ground. In the balloon and glass rod and cloth experiment, I have demonstrated charging by contact. Then, would it be possible to charge objects without contact? Yeah, actually this process is called charging by induction, where you induce the movement of charges through the attraction and repulsion of charges. As demonstrated in this diagram, the positively charged glass rod attracts the electrons on the pith ball and induces an electrostatic charge. When we think of charges on an atomic level, we call them point charges because we want to treat them as a point on a plane. Charges are scalar quantities that can simply be added together. As you would expect, positive charges have a positive value and negative charges have a negative value. So, the total charge on an object is all the positive charges added onto the negative charges, or the sum of all the protons and the electrons. The total sum of the charge is always a quantized integer value. Getting a fraction of a charge is fundamentally impossible. The total charge of an isolated system is always conserved. Charge can neither be created nor destroyed. It can only move from one place or object to another. Each charge has a value of approximately 1.6 to the 10th of the 19th power coulombs. The C stands for Coulomb, and 1 Coulomb is defined as the amount of charge flowing through a wire in 1 second. So in 1 second, all the electrons flowing through the wire is the value of 1 Coulomb. So you can imagine one individual electron has a very small charge. Now that we have a good understanding of what charges are, let us delve into how charges can interact with other objects. This equation below is the Coulomb's law, and it describes the amount of electric force produced by two charges. So F is the electric force, and much like other Newtonian forces, such as friction and tension, it has magnitude and direction. K is the Coulomb's constant, and it has the value of about 9 to the 10th of the 9th power. And Q is the charge of the 2-point charges, and R is the distance between the 2-point charges. So let's delve into the meaning of K and the implications behind it. So K can also be defined as 1 over 4 pi epsilon naught, and this is a constant value. 4 won't change, pi won't change, epsilon naught won't change, and so this would be equivalent to about 9 times 10 to the power of 9. And so what exactly is epsilon naught? So epsilon naught is also known as the permittivity of free space. And it has a value that you just don't need to know. But the permittivity of free space represents the capacity of a vacuum to permit electric fields. So if we look at Coulomb's law, we have K, which basically tells you how electrons flow in vacuum. We have Q, which tells us what are the values of the charges of the 2-point charges. And we have R, the distance between the two charges. So if we use the magnitude of the charges, how charges flow through a vacuum, and the distance between the charges, we can derive the force between these two charges. As you may have already observed, Coulomb's law is strikingly similar to the equation for gravitational force. The main difference here is between the two constants, K and G. So K actually is much greater than G. So by comparing these two constants, it is clear to us that electric force is a much, much stronger force than gravitational force. Let's go back to Coulomb's law and try to understand it better. So R on the bottom is the distance between the 2-point charges, and it is squared. So this means that the force will decrease exponentially as the two charges move further apart. And Q on the top basically just tells you the bigger the charge, the stronger the force. According to Newton's third law, every action will have an equal and opposite reaction. Electric forces obey this law as well and must have an action and reaction pair. So two like charges, such as two positively charged protons, will experience the same magnitude of repelling forces. And two opposite charges, like a proton and an electron, will experience the same magnitude of attractive forces. Like any other force, electric force can be superimposed. So if you have multiple charges, simply add up all the forces created by those charges. So let's say your proton is pushing another proton away, and you have another proton pushing the same proton away. And so the net charge on that final proton is the sum of those two other protons pushing it. Thank you all for watching my first ever video. Please like and subscribe to help the channel grow. I'll see y'all later.